go from current slide. And where we are is, at least by my mark on the page, is we were just about to get started on the error function. And I'm not... The last thing we did, if you recall, was dealing with, one of the last things was functions that you actually can't solve, okay? And that you leave them in an integral form. Okay. Okay, we normally don't, but I had a doctor's appointment this morning, so we're having class now, making it up. No problem. I knew she and another woman sometimes come in here and study before the biology class, so I hadn't even thought about that as a ramification. But anyway, and this is one such function that there is no analytic solution to. It's called the error function. And then it has a partner function called the complementary error function, okay? And here is what the error function is. Let me get my pen set up. And the only reason I'm even doing anything with it is that it comes awfully close to something that you were just talking about, okay? I'll explain in just a minute, okay? It's 2 over the square root of pi. That sounds interesting, doesn't it? Times the integral from 0 to x.
Does that say E R f of x?
Yeah, E R f of x, yeah. Error function as a function of x. E R f, so that means error function of x, okay? X is your variable here, e to the minus t squared dt, okay? Now, try to your heart's content to solve that integral. Try any technique that you have. You aren't going to do it, okay? That is has no analytic solution.
You can't do a U substitution?
You can try. If you did, that you would probably be the minus t squared, and du would then be minus 2t dt. You don't have a minus 2t in there. Okay, that's a transcendental function with no analytic integration for it.
What if you did negative 2 dt, right? And then you make it you divide dt by, or you divide
du by negative 2t. Well, there you got a t mixed in with the u. They're not separated.
Oh wait, 2t. Oh yeah, that wouldn't work.
Yeah, right. I know.
Yeah.
It's not solvable, okay? Believe me. Yet you use it all the time. You benefited from it last term.
What?
This describes a Belf curve. That's how your 39 became a C. Okay? Because of this function right here. And what they did was standard deviations and stuff like this. If you're in the middle, you got a C. If you're out here, you got B. And way out there, an A. Over here, a D. Over here, an F. I assume they did a full bell curve. They may not have, but that sounds like what they did. Okay? And so wherever you fit on the curve, that gave you your grade. That's riding the curve, they used to call it when I was in school. Okay? Now, it has a partner function that's this one. It's called the complementary error function. And I always forget where they put the C. ERFC of x. It's the complementary error function. Seems like the C should go in front, but they don't. And that is 2 over square root of pi times the integral from x to infinity of the same argument, e to the minus t squared dt. Okay?
That's the same problem.
Say again?
Isn't that just the infinity?
Yeah, it flips the things around. So the one, basically, it describes half of a bell curve. If your distribution was like this, and your x was here, this is the first one, and this is the second one, whatever is left over. Okay, so that's why it completes it, because when you add 2 together, you have all the space that you need to deal with. Okay, and basically that's describing this is the part under the curve, and this is the part under the curve beyond whatever your value of x was. Okay.
So, like, you have this side, and then the other side,
yeah,
where the y-intercept is at the peak of the.
Would it be
is
what?
the y-intercept the peak of the bell curve? Like, that would be the c's.
Okay. Actually, the bell curve does the same thing on this side. You know.
So I'm saying is the y-intercept the I guess what the c's are.
Oh, okay. That would be, if you get into statistics, that would be the mode of your distribution. The thing that happens most frequently. Yeah. And this gives you the other. And, you know, what is it? First standard deviation incorporates 50-some% of the things, and then the next standard deviation gives you the next part. Everything beyond that is pretty small, like 1 or 2% or something like that. So if someone's grading on the curve, there is very few A's, just a few B's, lots of C's. It's about the same number of D's as B's and about the same number of L's as A's. So sometimes grading on the curve is bad. They may actually pull a decent grade down because, well, but you're bottom of the class, so you get an F or a D. So sometimes you don't want to be on the curve. A lot of times they don't do that to people. They have enough people screwing off that they get the F's, you know, and you don't have to.
Why do they do modes and not means?
What's that?
Oh wait, means average, right?
No, C is average.
C is average?
Should be. Yeah. And that's where your main distribution would lie here. And then the next standard deviation would be here, and then the remainder is out there. So anyway, that may not be exactly it, but it is pretty close to it. Now, it says from the known result, and this is why it's not exactly the bell curve. Let me go on and get rid of this part, because that's just getting in the way of my writing here. It says from the known result that the integral from 0 to infinity, how they know this, of e to the minus t squared dt is equal to the square root of pi over 2, okay? Now that somehow they think we all know, but it is true. Then by dividing by square root of pi over 2, or other multiplying by 2 root pi, then these two add to be 1. So putting the 2 over root pi in front, and then doing this 0 to infinity, that would be adding those two together, e to the minus t squared dt would equal 1. Now, that's why it's not quite the bell curve. It's pretty close to it. But what you have there is it's just 1/2 of the population being 1. If you included the other side, which is what we usually do, is then put the mean up here as, I believe it's minus t squared plus or minus mu or something like that, then that shifts it over, and then your bell curve does everything. And that's what usually happens. Your mean is not usually 0. The mean is usually somewhere down there. So, but anyway, then you see that these two added together produce this one, and they add to 1. That's the whole purpose of what I'm doing. So that means the error function plus the complementary error function, when they add together, you get 1. Okay. Because of its importance in probability, statistics, and applied partial differential equations, the error function has been extensively tabulated, and that's what people use. They've done numerical calculations of this, solving that differential, that integral numerically, and they have tabulated results to as many decimal places as probably you want to ever get. But the error function of 0 is 0, is one obvious function value. Now it says numerical values of the error function can be found using computer assisted system, or however they call that, such as Mathematica, probably the one you're naming. MATLAB probably has this on it too. I know you enjoy that, so you could go find it.
I don't even know how to open it up.
What's that?
I don't even know how to open it up.
All right. If we're solving an initial value problem and they said number 6, that was back, pages ago, bottom of page 57, that's your standard linear differential equation like that. If you're solving one and recognize that indefinite integration on the right-hand side would lead to a non-elementary integral, meaning one that you cannot solve analytically, then over the interval, it's convenient to use the definite integration as your answer. So here's an example of what they're saying, and it's not very satisfying in my mind, but I guess we have to show it. So here's your example 7. Now we didn't do that. No, I don't think we did this one. Okay, solve this. dy dx minus 2xy is equal to 2, with an initial value of y of 0 is equal to 1. Okay? Now, I know it's been a long time, but you remember how to do one like that?
Yeah, we find the p of x and take the interval.
Say that again.
We do the interval of 2x.
Yes, that's exactly how you begin. That's your p of x, so you do the integral of minus 2x dx. Okay? And what does that give you?
It's just going to be x squared over 2.
Over 2.
Well, so it's just
say again?
Negative x squared.
Right. So it'd be negative x squared. Perfect. And then you do the e of that. Okay? And that's your integrating factor, your mu. And that's what you multiply by both sides. You say e to the minus x squared dy dx minus 2xy e to the minus x squared y. Wait. No, I already put the y in there, sorry. Is equal to 2e to the minus x squared. Okay? Now, supposedly this, and this is something I always check and see, should be a perfect derivative. It should be a d by dx of something. It's not letting me write down there because that's where your symbols are. Okay? And that should be the perfect derivative of e to the minus x squared times y. Now that's what it should be. Let's confirm that it is. Well, it's the first times the root of the second. That's got it. Plus the second, which is the y, times the root of the first. So the root of the first is e to the minus x squared times chain rule of minus 2x. Yes, that is exactly what we've got here. And this is equal to 2e to the minus x squared. All right? So then if we integrate both sides, or write it in differential form, and then integrate both sides, okay, what we have then is the integral of a derivative is just what you got, e to the minus x squared y is equal to 2, but here we have this integral we can't solve, e to the minus x squared dx. You can't solve that. That is a non-elementary integral. There's no analytic solution. But it's kin to the error function. Okay? All you need is a 1 over root pi. And that would be exactly your error function if you're going from 0 to x. And you change the what you want to call it, to t's. Okay? The dummy variable to t's. Okay? Now, that gets us right up to that first equation there. And what they've done in addition to what they've been doing before, and it sort of seems artificial to do it, but they are. They're going from 0 to x, and that changes the they're doing it down here. Okay. Yuck! Wait, say again?
What if they, can the problem be solvable if they gave us like a y0 equals like...
Well, they gave us this, but it's still not solvable. Okay? We'll see. That's where we're heading now.
Well, 0 equals, if x equals 0, wouldn't it just be, that'd just be 1.
Okay. Okay, we're going to do that. We're going to do that very thing. In fact, what I think I'm going to do here is back up just a little bit, because I sort of jumped ahead here. We're going to go back to this step down here where I said you integrate both sides. And when you integrate them, you put limits on here. 0 to x. We never have done this before, but we're doing it now. 0 to x. And that changes the argument here to a t and a t and a t. Okay? So I should have taken that off while I had my eraser going. This is minus t squared dt. Okay? Because you need, okay. Well, this thing is the perfect derivative of thing of an integral of a perfect derivative. So this just comes out being this, but you're going to evaluate it when t is going from 0 to x. Okay? So that's what I'm going to do up at the top. And that would be e to the minus t squared y evaluated from 0 to x. And that's the value's t, not the y. Okay? And this is equal to 2 times, and that's the integral we don't have. Okay? And actually, I want to write that as 1 over root pi times the error function, but they're not doing that yet. They're just leaving it alone for now. 2 times the integral from 0 to x of e to the minus t squared dt. Leaving in integral form. When you evaluate this, that will be e to the minus x squared y minus, when you put a 0 in there, you get 1. So it's just basically minus a y. And I don't, yeah. Well, okay. Back up just again. I sort of left something out here. I forgot to evaluate my y at x at those values as well. So it's e to the minus x squared y of x minus e to the 0, which is 1, y of 0. Okay? And that's equal to 2 times the integral from 0 to x of e to the minus t squared dt. Okay? Now, the y of 0 is equal to 1. So what we have here is e to the minus x squared y of x minus 1 equal 2 times the integral 0 x e to the minus t squared dt. Okay. Now, what they do now is multiply both sides of the equation by e to the x squared. So that will wipe this out. So you have y of x minus e to the x squared is equal to 2e to the x squared times this integral from 0 to x e to the minus t squared dt. Okay, this just gets really a little bit on the awkward side, but it's okay. Then you can add the e to the x squared to both sides, so that gives you y of x is equal to e to the x squared minus 2e to the x squared. That's pretty ugly there. Okay, times this integral. I wish they'd call it and write it, but they're carrying it along as if it's the most valuable thing ever. dt. Okay? Now, they do that and then factor out, I'm running out of room, y of x is equal to, they factor out the e to the x squared, and that leaves us a 1 minus 2 times this integral, 0 to x e to the minus t squared dt. Okay? Now, what they hope you notice here, this is very close to being the error function. If you had a 1 over root pi there, that would be the error function. So what they do is put a root pi in front of it. Okay? Now,
Wait, they put it in front?
well, yeah, okay. I'll try to explain it in a minute. Let me get some room at the top of the page to write again. I've just used up too much room. Hopefully we won't need to go back here. I sure hope not. I've been trying to make sure we're all right with it. Okay. Now, if you'll notice what I did here to answer, okay, this thing here is almost the error function. You already got the 2 in front. All you need is divide it by root pi. So if you divide that by root pi and multiply by root pi, that's multiplied by 1, right? So that's why you put the root pi out front. So this is just your error function. That's exactly your error function. So what you have here, your y as a function of x is e to the x squared times 1 minus root pi times the error function of x. Okay? Now, as strange as it seems, this is the graph of it. Now that doesn't look anything like a bell curve. Well, because you've got all this other stuff multiplied and messed with it. So yeah, it comes out very. The thing that takes over is it's e to the minus x squared. It takes off and goes. In fact, I don't see how it ever becomes negative, but it seems like it does. Because I didn't think the error function was ever negative. So I can't quite explain how this winds up being negative. Because e to a negative number is positive still. So I don't know, it's beyond me. But anyway, that's what they claim is the graph. And it sure enough goes through the point 0 to 1. X equals 0, y equals 1. Okay. And that's all they do with it. It just seems like it's almost, as Betty White said of Facebook, when she got her Academy Award for playing in some movie that dealt with Facebook, she said, before I was in this movie, I didn't even know what Facebook was. Now that I know about it, it seems like to me it's a tremendous waste of time. So that was the typical Betty White saying. Seems like to me this whole problem and exercise here was almost a tremendous waste of time, except to introduce you to a pretty famous and very much used formula, the error function. Now, I can't even tell you why they call it the error function, but that's the name that's been given.
Can you please not put this on the test?
What's that?
Can you please not put this on the test?
I can't hear.
Don't put this on the test, please.
Oh, it's not going to be.
Okay.
Yeah, okay.
That just went over my head.
Yeah, well, it's, you can't do much with it, but I guess the point is, that's a pretty innocent looking differential equation, isn't it?
Yeah.
But then when you start dealing with it, you find out it has an impossible solution to solve analytically.
So if it was a plus 2, would it be easy to solve? Plus 2xy?
Yeah, I think that would do it. I mean, I don't think you'd have this problem then, okay? You might have a different problem, but you wouldn't have this problem. But the thing is, the error function is a very well-documented function. Like they said, there are tables you can look up anywhere. So even if you had this, you can go on any mathematical package like MATLAB or Mathematica, or there's several others out there, and just type in error function and it comes up. In fact, on graphing calculators, you probably can do an error function key. I don't know, but my guess is you can. It's that well known of a function. So no one ever goes around solving it. They just use the results. Like good engineers, right? Okay. All right. And that did finish the section. Now, these remarks at the end of the section, first time I taught from this book, I thought I needed to go over them. They just drag on indefinitely. But let me just put a couple of things to you. It says, mathematicians have adopted their own certain words from engineering which they found appropriately descriptive. The word transient, okay? Now, not in this context, but in many contexts when you have a function like this, e to the minus x squared, that's in your answer somehow, that's a transient. Because as you get large x's, this thing's going to 0. So it's not going to have a big influence on it. So that's called a transient function. Okay? We did that one earlier. In future discussions, we'll use words like input and output. They will occasionally pop up. The function of f in equation 2. So if we go back to equation 2, that's the one that's our parent equation here. dy dx is equal p of x, y equal f of x. Here your f of x is 2. Okay? That f of x, they give the title of your input function. Okay? Or your driving function. Solution of y of x of the differential equation for the given input is called the output function. So whatever your y is at the end, this one, that's your output function there. The driving function was a 2, okay, and it has reasons for being there, and your output function is that. There are termed special functions, and here's a couple more. The sine integral function, that's called SI f of x, sine integral function. And then there's a Fresnel sine integral function, which I think they use subscript F for. So you have all these things out there. You'll find that in many areas there will be specialized functions that they use for that particular area. Okay? And sine integral and Fresnel sine integral have some special case uses out there, and if you happen to be dealing with problems that use those, you need to know. But otherwise, and usually you'll get familiar with them if you need to. So anyway, that's it. I think I assigned most of these before. Do any of the odds that are in the back of the book, 1 through 23. Do any of the odds in the back of the book between 25 and 35. Do any of the odds in the back of the book either 37 or 39. Do 41 if it's back there, 43 if it's back there, 45 if it's back there. And here is the sine integral function. Number 47 is a sine integral function. And it's capital S, little I of x. I thought it was f of x. There it's not. Capital S, little I of x. And it's the integral from 0 to x of sine t over t dt. Try solving that one. There's no analytical solution for that one either. Okay? Then the Fresnel sine integral, and that's just capital S of x. They don't do the integral, the I for integral there. It's the sine of pi halves t squared dt. No way to solve that one analytically either. Okay? But they have tables full of them that you can access if you need them. The discussion problems, you're certainly welcome to look at those. Most of those are not in the back of the book, but you can take looks at them if you want to. Then there's some mathematical models, radioactive decay. We talked about that a little bit. Doubt if that's in the back of the book. And then if you have a computer package, like your good old MATLAB, and you want to do some of these problems on that, knock yourself out. Okay? But you don't know how to turn it on. Okay. So let's go to, that finishes 2.3. Any questions? That's your general linear differential equations. And I would say use it only if you can't separate the variables. If you can separate variables, that's always the easiest. And there's actually a little acronym or acrostic or something that a student told me about once, I can't remember it now, that basically gave the order of looking up these things. Separable was first, was linear second. It spelled some little word. I don't remember what it was now. Maybe I'll...
You want me to look it up?
I don't know. It's not worth it, but if I think of it, I'll tell you. But I'd never heard it, so it wasn't necessary to know, but it was a clever little thing. All right, let's move to 2.4 for exact equations. Now, this is a simple first-order differential equation but it's written in differential form. Y dx plus x dy is equal to 0. Now, it's separable in the fact you can do this. Y dx is equal to minus x dy, and then divide this side, both sides by y, and both sides by x. Okay? The y's go out here, the x's go out here, and you have basically natural log of x is equal to minus the natural log of y plus c. Okay? And you can bring those, back together and say the natural log of x plus the natural log of y is equal to c. Well, this is the same as the natural log of x times y is equal to c. And then you can exponentiate both sides, and you get xy is equal to e to the c. Okay? Or just c. Okay. Now, so f of x is equal to xy. Okay? Your f of x is equal to xy. And then you can go back and do all this. Very easy to solve problem. Okay? Now, in this section, we're going to examine, and basically, it's also a linear. Now, it doesn't look linear maybe here until you do some other adjustment to it, like not writing it in differential form and writing it as y plus x dy dx is equal to 0. Then rearrange the order a little bit. X dy dx plus y is equal to 0. Then divide everything by x. Okay? And you have dy dx is equal to plus 1 over x times y is equal to 0. Here's your p of x, and you're ready to go to town. It's perfectly doable. You integrate p of x, you get log x. You take the e of that, you get x, and then you have, you'll get the same answer. Alpha of x equal xy plus some constant c. Okay. So, pretty simple form. But in this section, we're going to examine some first-order equations written in differential form that is a bit more involved. So let me go back to that. Now the key is written in differential form. Here's going to be the standard form. M, some function of both x and y, times dx, plus some n of both x and y, dy, is equal to, and it's always going to be 0, or at least for a while. I don't think we're ever going to have a constant out there. It's going to be 0. If we do have a constant, we'll deal with that later. Okay. Now, as you might guess, you can make that m of xy and n of xy complicated enough. There's no way you're going to be able to separate the variables. No way, especially if some of those y's are at certain powers, no way it's going to be linear. Okay? So, this can easily be something we can't solve separable and we can't solve linear. So we need a new method. There are certain conditions for these functions there. If they fit the conditions, we call them exact equations. If they're exact equations, we have a method for that. So that's what this section is going to do, is talk about how you can solve fairly complicated looking expressions like that. Now, if you're following, I don't mean to put you on the spot, but are you following what we're doing in Cal 3? Okay. You know we've gotten to the portion where we're taking derivatives of more than one independent variables.
Yeah,
partial derivatives, exactly. So if you're up to that, you're fine, because that's what we're going to be using here. Okay? And they're going to jump into something here and start throwing partials around. These are just being used as a tool to solve an ordinary differential equation. We're not into partial differential equations yet, but we're using partial differentials to solve an ordinary differential equation. Okay? It's a little bit of a distinction there, but it's fairly important. So let's just say we got this function z that is a function of both x and y. Just like that m is a function of x and y and the n is a function of x and y. You have multiple variables in those expressions. Okay? Now, so let's say that z, which is a function of x and y, is a function of two variables with continuous first partial derivatives in a region R of the xy plane. So, we've been doing this. I don't know if you've gotten there yet. If you do dz, now that's a differential of z. Okay? Differential of z is then the partial of f with respect to x dx plus the partial of f with respect to y dy. Okay? Now, that's what your dz is. That's just your standard differential form when you have partials in there. Well, look at this. That looks a lot like your m of x. That looks a lot like your n of x because it's preceding the dx and the dy. So in the special case where this f of xy here, that d there, happens to be a constant, then the dz is going to be 0, and now you're exactly that form that we have there. It seems like a lot of coincidences, doesn't it? But that is important here. In other words, given a one-parameter family of functions, f of xy is equal to some constant c. Now we're going to start with that. This family of functions, f of xy, is always going to be the same constant c. Then you can conclude this. The partial of f with respect to x dx plus the partial of f with respect to y dy is equal to 0. Okay? Now, we can generate a first-order differential equation by computing the differential on both sides of the equality. So what if this was I think I need more room, so I'm going to erase this, but keep in mind what we've got there, okay? We're going to try to come back to that. What if you had this? X squared minus 5xy plus y cubed is equal to some constant, okay? Now, if you think about it, a lot of equations you'll have, wherever they come from, they're either going to be something that's equal to 0, or something plus something another is equal to 0. And if you can take the constant and add it to the other side, or subtract it from the other side, or whatever you're going to do with it, then it's pretty easy to imagine coming up with equations of this form. That's nothing that unusual, right? Okay, so let's do what they just said. This is an equation that if you take the partial of this thing with respect to x and multiply it by dx, so let's do that. What is the partial of this thing with respect to x? 2x
minus 5y.
minus 5y. Perfect. That's the partial of this thing with respect to x. Now do the partial of that same thing with respect to y.
Minus 5x plus 3y squared.
Minus 5x plus 3y squared. Okay? Take this thing, that's the partial of that, multiply it by dx, plus, which in this case actually, well, yeah, let's leave it a plus. I'll put it in parentheses. This dy, that's equal to 0, because when you take the derivative of the constant, partial of the constant, you get 0. Okay. Now that is a form we call a differential equation, as opposed to the derivative equation. This is a differential equation, a true differential equation. That thing is not going to be separable, mostly because of those plus and minus signs. Okay? So, begin to aggravate me. I think I'll take it off. So the blood work for him this morning. I could have taken it off a while back.
Now you're feeling lightheaded.
What's that?
Now you're feeling lightheaded.
No, it's just that I was teaching my arm.
Yeah.
Pain in the neck or arm or somewhere. So I hate throwing that into the trash. Not that it anything wrong with it, except it had a little spot of blood on it, you know, and that really should go into biohazard. Yeah, biohazard, but I'm not.
It's just
Yeah,
blood.
it's just a little bit, and I don't have anything that anyone is affected by. Okay, so now they say again, this looks a lot like m of xy. That's a function of x and y, dx plus n of xy, that's got x's and y in it, dy equal to 0. Now, they make a little statement here. Of course, not every first-order differential equation written in that form corresponds to f of xy is equal to 0. This one does, okay, because that's where we got it. But not everyone will.
So you
okay?
would add them together, though?
What's that?
You would add them together?
Well, you can't really, because this is dx and that's dy. So, no, they're pretty much, not much you can do with them here, except leave them like that. Now, not always will that correspond to a function f of xy is equal to 0. If it does, then we can proceed using this. If it doesn't, we can't. So what we need to do for our purposes, it's more important to turn the foregoing example around, namely that if we're given an equation that is like this one right here, and we know that one came from it, is there a differential equation that you did the d of this thing, that's your z, is there one, okay, that's equal to c? And here is the first definition, and you have your book on an e-book, okay?
You can pull it up.
But I'm not sure everybody does, so for those listening at home, I really appreciate that you're here, because I would be bored to tears talking to myself, so I'm glad there's someone to interact with. Okay, here's the definition of an exact equation. Differential equation, I'm just going to call it a DE, a differential equation, differential expression, so let me change it. A differential expression okay, of m of xy dx plus n of xy dy, okay, that's just an expression, is an exact differential, okay, it's an exact differential in a region R okay, of the xy plane, they just write xy plane, okay, if it corresponds to some function f of xy defined in R, okay, that's what it is. That's the sentence. A first order differential equation of the form m of xy, now it's a differential equation, m of xy dx plus n of xy dy is equal to 0. Now, so far they're all equal to 0. Is said to be exact equation, just a new term, exact equation, if the expression on the left-hand side is an exact differential. If expression on LHS, left-hand side, this right here, is an exact differential. Sounds like they're talking in circles, doesn't it? Okay, exact differential. It's an exact differential equation if the expression on the left is an exact differential. All right, what do they mean by that? Okay, I think I'm going to start over again on a clean page so we'll have room to work. X squared y cubed dx plus x cubed y squared dy is equal to 0 is an exact equation. Okay. Now, not just that, that one's separable, right?
Yeah.
Because you don't have the pluses and minus sign, you put the second term on the right-hand side with the minus sign in front of it, and then divide by x cubed and y cubed, wipe them all out. That's separable. It's totally separable. But it's also an exact equation.
Now, if you do the partial derivative, what's that x value on the first one, on the dx? Is that x to the... That's
x squared.
That's x squared? Okay.
Yeah, x squared, y cubed,
when you
dx.
do the partial derivative, it would be 2x y cubed.
Okay, it depends on what you're taking it with respect to.
X.
Okay. Yeah, if you're taking it with respect to x, but we don't usually do that. Okay? It came from there, maybe, that it is a partial of something. That's what our assumption is. In fact, that's the next thing that we're going to do. But we're not going to take the partial of that with respect to x. What we're saying is, if that is the partial with respect to x of some other equation, and we're going to see in the very next line what it is.
But isn't it kind of already in, standard form?
Okay, that's in the standard form of an exact equation, and it is an exact equation. And here's why. Because the left-hand side is an exact differential of this, and you're thinking in the right direction, but it just said it a little bit If you did, yeah, 1/3 x cubed y cubed.
Why is that?
Okay? Because take the partial of that. Take the partial of that thing.
You should say squared.
With respect to x dx plus the partial of this thing with respect to y dy, and see if you don't get exactly that thing up there.
Yep.
Now, yeah, that gives you
X squared.
y cubed dx plus,
Wait, doesn't the dx cancel? No, I'm so sorry. That would just be. Ooh.
what would that be if you took the partial of that with respect to y?
1/3 x cubed plus.
Okay, you sort of fade it out at the end. Wouldn't that be
1/3 x cubed.
X cubed
Y squared.
y squared? Because the 3 you come down wipes out the 1/3.
Okay.
Right, okay, dy. And there you have it. This is exactly what you have up here, okay? So that is a different exact equation because these are the components of an exact differential. But you had to know what equation it was coming from. Now that one wouldn't require too much effort to come up with, but in this case, this is your m of xy, this is your n of xy, okay? All right. Now, here's the test. And they sort of pulled it right out of the air here, okay? Here's how you tell if it's an exact equation. Take the m of x and make the partial of that, not with respect to x, but with respect to y. And that's what I thought you were heading toward when you said the other statement. You said you don't want to take it with respect to x. Take this one with respect to x. Okay? See what you get. What is the partial of this thing right here with respect to y?
3x squared.
3x squared y squared. Perfect. What is the partial of this n with respect to x?
3x squared y squared.
And those are exactly equal to each other. That's the test.
But don't they have the dx attached to them?
What's that?
Wouldn't they have the dx and dy attached to them?
Yeah, but this is a test to tell you whether that expression is an exact expression. We know it is because we know exactly where it came from. It came from this one right here. We know it's an exact expression. Okay? Now, we're going to test it and say, what happens if you take the partial of the first one, not with respect to x, but with respect to y, take the partial of the second one, not with respect to y, but with respect to x. If you get the same thing for both of those partials, you know your original thing was exact. Okay? So you don't have to be able to dream up what it could be the exact thing of. We're going to do that later. Okay? All you have now is to confirm whether it was exact or not. This tells you it's exact. That's exactly what the next theorem is going to give us. Okay? Now, I forgot to pull out my watch. We can't run over. Okay? Because
12:13.
oh yeah, we got an hour. Okay, good. You need a break?
You can take one.
Huh?
You can take one.
Okay, well let's finish this theorem and then we may do that. So let's erase this. And here's theorem 2.4.1. Oh, you want it now, huh? Okay, okay. You sure have a way of expressing yourself. All right. Let m of xy and n of xy be continuous and have continuous first partial derivatives. Partial derivatives in a rectangular region, in a region R, defined by A is less than X is less than B, and Y and C is less than Y is less than D. Just some rectangular region. Okay? Okay. Then a necessary and sufficient condition. That means it's absolutely perfectly copacetic to have that m of xy dx plus n of xy dy equals 0. No, they don't do this. They just call it an expression now, not an equation. Then this thing right here what happened to my pen? There it is. Okay. Then this thing right here is an exact differential if partial of m with respect to y is equal to the partial of n with respect to x. That's all you need to show. So if you're given a form that looks like it has potential to be an exact differential, here's your test. Do the test. If the test passes, it is. If it doesn't pass, it's not. You have to use some other method. Okay? But if it is, you can go with it. Now, so far, all we're getting is to determine if it's, if it is. That doesn't tell you anything about how you solve it. Okay? It just tells you whether it's exact or not. Okay? They go through some proof here. They say necessary and sufficient. They prove the necessary part first, and then they talk about the sufficiency part. Okay? Now, all that does is set you up and lets you know, yes, you have an exact differential equation. What it doesn't tell you is how you solve that exact differential equation. That's the next thing we're going to do.
So basically we're just trying to get it like that last problem, get like them equal to each other.
Say this again.
Basically like what we're doing like we did last problem, we swap the dx's and the dy's to get them equal to each other.
Dx and dy's.
Like we, instead of like, we switched on the last problem where it was like 3y squared or x squared and
we were doing exactly the same.
Yeah.
Taking the partial of the first with respect to y, the second with respect to x. If they're equal, yeah, you've got an exact differential.
But if it's not, we're going to...
If it's not, we're going to talk about that later. Okay. But if it is, then it's solvable. But we don't know how. Okay. So that's what we're going to head into now. Once you've determined it is an exact differential equation, then what are the techniques for solving it? And this is where, middle of page 66, method of solution. All right. Now this is sort of long and involved, but just sort of keep your head about you, okay? Keep up with the trees, but don't get lost in the forest, okay? Just keep up with what you're doing, okay? Now, we're going to assume that we have an equation in differential form. So let's start over. Have an equation m of xy dx plus n of xy dy equals 0. Assume we have one. Okay? Now, the first thing you do is determine if your equality holds. Okay? First step is partial of m with respect to y equal to partial of n with respect to x. If yes, then proceed. If no, for right now, hang it up. It's not going to work. But if it's yes, if that partial is true, those two partials are equal to each other, then here's how you solve. Okay. Now, remember what our whole assumption here. There is some function f of x and y that's equal to a constant. Okay? That's the assumption. There is that. Okay? Now, if that's the case, remember where we started, the partial of that f with respect to x, that's going to be your m of xy. That's how we set it up to begin with. That's going to be the case. Okay? Now, that's itself a differential equation, right?
Yeah.
Okay? So how we're going to go about solving this is write it in differential form, which is df is equal to m of xy dx. Okay? Now, I'm sorry, that's a partial there. Okay. And that's a partial there too. But we're going to treat them as if they're not partials. So we're going to write them like this, assuming we only have f as a function of x. We're going to hold the y's constant here. We're going to integrate both sides of this. Okay? Now, but we're only integrating with respect to x. Now there, we haven't gotten this far in Cal 3 yet. How you integrate, do multiple integrals. We're only doing one here, but we're only integrating with respect to x. We're treating the y as if it's a constant. Okay? When your dx out there is a dx, you're going to treat your y's as if they're a constant. Okay? And you're going to integrate that as best you can, but then when you do the integral,
wouldn't it just be mxy?
What's that?
mxy?
Yeah, but you see, you're only integrating with respect to x, so you're going to just treat your y's as if they're constant. Same thing as you did when you're taking a partial. Partial with respect to x, you treat the y's like they're a constant. You take only the partials of x, the derivatives of x, right? Mm-hmm. So now we're going to the reverse of that, only integrate with respect to x, but normally when we integrate an indefinite integral, we have a plus c, right? Not anymore. Now what we're going to have is not just a c, but some function of y alone. Because you're treating your y's as if they're a constant. So don't just put a plus c out there, put a g of y out there, or some symbol for y. Don't use f because you've already used f or anything else. So g of y is perfectly fine. Okay? Now, there's your f of xy. The integral of a perfect derivative is f. F of xy is equal to that thing. Now, we haven't solved the integral yet. We just wrote it down, right? Well, what are we going to do next? The partial of this with respect to y is going to be your n of xy. Remember, that's how we got it all started. Okay? So we got to integrate this with respect to y. Okay? Well, if we're taking the partial of this, that'll be the partial of this with respect to y, plus, and this you don't have to write as a partial because this is only a function of y. So you can write that as d by dy. Okay? This might seem like it's getting a little bizarre to you, but it's really not that bad. Promise you. When you do it in practice, it'll work out that way. Okay? And this then is your y prime. I mean g prime. That last term there. That's what the book's calling it. Okay. So where do you go from here? Here's your g prime. That's this term here. And what this is your n of xy, which you were given to begin with. You already have confirmed this is a exact differential. So this n of xy that you were given at the very beginning, subtract from that your partial with respect to y of your integral of m of xy dx. Okay? Now, you, I don't know why they threw it in and did the g prime when it says integrate that, which means, right, this is dg dy, which we had to begin with. Huh?
Would it be g prime of y?
What's that again?
Would it be g prime of y?
It's g prime of y, but let's call it dg dy. That's a better thing. Take this thing, multiply it by dy, and then you have dg dy, and integrate that. Now you're integrating with respect to y. Okay? So this is a dy here, and this is basically a double integral of your m of xy. Okay? Now, using all these symbols actually, to me, just muddies the water. What we're going to do is go back and actually do one. And then hopefully you can see how all the pieces put together. So before we do that, they do make another observation. Secondly, we just as well could have started with the partial of f with respect to y being your n of xy and gone that route. Okay? You do whichever one is easier to do your integration. Okay? If one of them looks impossibly difficult, then switch it around. Okay? And they come up with these solutions, and then they say, don't memorize them. Just do them. It's the technique. It's the process. It's not some memorable thing at the end. So that's what we're going to do. We're just going to do the technique. Okay? So here is a differential equation. 2xy dx, pretty exciting, isn't it? Okay. Plus x squared minus 1 dy is equal to 0. Okay? Now, so far, it's looking okay. You have some expression here of x and y dx. Some expression here. Now, even though this doesn't have a y in it, you can still say it's an expression of x and y dy is equal to 0. So far, that's got to be a 0. But we don't know if this is exact or not until we do our test. What is our test?
Take the partial.
Of what?
2xy with respect to x.
With respect to what?
X.
The other one. Y. Okay? And what does that give you?
It'd just be 2x.
2x. Perfect. And you do?
Dx.
Yes, with respect to x. And what does that give you? 2x. Ding, ding, ding. This is a perfect. This is an exact differential, so we can start our process that we were discussing on the previous page and just got so bogged down with it, it was just about incredible. Okay? So let's start. And here's your assumption. There's some function out there, because this is exact. There is some function out, f of x and y equal to some constant c, that when you did these things to it, you're going to get that. Okay? That's your first assumption. Okay? So let's take the partial of that f with respect to x, and that's going to give you your m. 2xy. Okay? Because that's where it comes from. Once you confirm that is an exact differential equation, that means there is some function f of xy equals c that is going to produce these things. So if that's the case, let's take the partial of this f of xy, and you know that's got to be. And we're going to do it with respect to x now. We could have done it with respect to y, we're just going to do it this way. Okay? Now, next thing we're going to do is write this as a differential. And this doesn't quite seem right, but we're going to do it. We're going to do df is equal to 2xy dy. I mean dx, sorry, dx.
Now is that df or is that partial d?
It should be a partial, but we can't take derivatives of a partial, so we're going to make them like they're x's for now. Okay? And we're going to integrate. Okay? Integrate with respect to x. So this gives you your f, which is both of x and y, remember. And what is this? Take.
It's going to be it's just going to be x squared.
Over 2. That wipes out the 2, so you have x squared y, right?
Yep.
Plus some function of y alone. That would have been your plus c. Now it's some function of y alone, right? Okay. Now, we're going to take the partial of this thing, that same f of xy, with respect to y, and know that's got to be your n of xy. Okay? So, what that gives us, and we're going to do the same trick to it, you'll make that d of f is equal to the integral, well, let me leave off the integral for now. Okay? Take the partial of this with respect to y. Actually, let me back off a little bit here. I jumped ahead. I don't want to do that quite yet. I really want to do what we just said. Take the partial of this thing with respect to y, and that's the derivative of this thing with respect to y. And this is going to be the partial of this with respect to y, which we know to be x squared plus 1, x squared minus 1. Because that is your n. That's your, no, I said it backwards. No, it's not that. Okay. Wrong thing. Okay. Not yet. We're going to come to that. We know what n of x is. This is your x squared minus 1. That is n. Okay. And that looks like we know what that's hemming toward, but we'll get there in a minute. Okay? Now, no, I'm sorry. You're not taking the partial of this. That is your n. The partial of that thing is your n of x. Okay? And that is what the n of x is. Okay. Whew. Knew that wasn't coming out right. Okay. Now we're focusing on this part here. Partial of this thing with respect to y is what? It's right here. Help me. Partial of that with respect to y.
That just be that just be x squared, wouldn't it?
Just x squared plus g prime, I'm just going to shorten it now, is a function of y alone, is equal to x squared minus 1. Hey, I think I can figure this one out. The x squareds are x squared. That's pretty obvious. This means g prime is equal to 1, minus 1. So what in the world would that be then? If dg dy is equal to minus 1, multiply both sides, write it in differential form, integrate, and what would that be? G of y is equal to what?
Equal to x squared. 2xy?
No, just this right here.
Oh.
What's the going to be y?
Yeah, it's just going to be just y.
Y. So that's a minus y. So now we just about have everything we need. Okay? Where was it we had written that? Right here. Before we took the partials here, we said f of xy is equal to, before we took the partial, x squared y plus g, and our g was now a minus y. Okay? And then here we can put our plus c if we need one. Okay? All right. So, oh, here's where some of their little comments get to me. Okay. So remember, before we did this, this is what we had. Before we did the partial with respect to y, partial with respect to y, partial derivative with respect to y. You knew that was equal to that. F of xy is equal to x squared y plus whatever your g of y is. Now here we found out what the g of y was. We put that back in. That gives you that. Then you put your plus c here. Now, here's the thing that sort of drives me nuts. Okay? Can I erase some of this? Okay. Whoa, that's the part I wanted to erase. Okay. Probably could erase more, but I don't want to take the time to do it. Okay. Now, there is a solution. All right. And notice the next thing they said. The explicit form of the solution is easily seen to be this. Okay. Easily seen to be this. Okay. Oh, I'm sorry. No, they didn't write it that way quite. They put it equal to C. And in that sense, yeah, that's okay. Oh, remember your f of xy, that's right, is equal to C. Okay. Now it's is making more sense. Okay? Now, you don't put it plus C at the end, you put equals C because that was your first assumption. Okay? Now, factor out the y, and that gives you x squared minus 1 equals C, so your solution is y is equal to C over x squared minus 1. Okay? And that is pretty easy to see. Now, the key here is x can't be plus or minus 1.
Yeah.
Okay, it can be anything left of minus 1, it can be anything between minus 1 and plus 1, or it can be anything right of that, but it can't be anything that crosses that. Your interval has to be one of those three intervals. And that kind of makes sense in the first place, because if it was equal to plus or minus 1, your original thing would just be 2xy dx is equal to 0, because that thing would equal 0. So this isn't unusual for that to be limited.
If we draw the domain, would it be negative infinity to negative 1? And
or minus 1 to 1, or 1 to positive.
Would they be parentheses or closed brackets?
Okay, they're the ors. They're the
Unison?
not unit. The other one. Intersect.
And?
Not and, or.
No, I'm talking about the one that looks like an upside down parabola.
Right. Okay, that's an intersect. It's either this one or that one or that one. It's not and. Union is the and. These are the ors. And here's the key. What if you had an initial value here? And what if at x equal 3, y is equal to 7, or whatever? Then you have to be on this line here, because x is equal to 3. You can't be here or here. So it's not either or. It's not both and. It's an either or. You have to be out there. Then you solve that one, and that will give you what that was. If when x equals 0, y is equal to something, that puts you in the middle between minus 1 and 1. You can't be on the other places because x has to be in there. Or if x is minus 2, you're over here. So your initial condition, besides telling you what the C is, it tells you which part of the domain you're in. And you don't have the liberty of being in any of the other part. You have to be in that part. So that initial condition does two things for you here. It finds the C for you, but it also tells you what portion of the domain you're in. Okay. For one like this. Not all of them will be like that. Do we have time to do example 2? Yeah, we go to 1:15, so we got 30 minutes, right?
I got the bathroom.
Sure. I'll take a break. Wow, this is slow coming. All right. So there was our final solution. Now, the solution is not f of xy is equal to this. That's not it. It's that f of xy, which is this, is equal to c. That's your solution. You have to have the c in there, okay? And let's see. All right, well, they just make another statement there. I think we have time to do example 2. All right, to clear?
Yes, sir.
Okay. So here's one. I have a feeling this one's not going to be linear. E to the 2y. Confirmed, that's not going to be linear. Minus y cosine xy dx plus 2x e to the 2y minus x cosine xy plus 2y dy is equal to 0. All right. Question. You think you can do that one by separation of variables?
No.
No way close. I mean, you can't even come close to that. You think that might wind up being linear?
No, because there's it's raised to the 2y exponent.
Yeah, e to the 2y, cosine of xy. Y is all tied up with other functions. It's not a naked y. Okay, so no way. Now, the only hope we have then of this one is if it's an exact. How are we going to be able to tell if it's an exact differential or not?
I don't know.
You don't remember the test?
The px? We don't do the px. We just set them equal to each other.
What equal to each other?
The two variables.
The two variables.
Yes, sir.
So y is equal to x. That's going to be this right here? I don't think so.
So we do the dx. We do the dx, right?
I don't know what you mean by do the dx.
Instead of doing the e to the 2y minus y cosine xy, we're going to do that one we're going to do the dy of that one, and the next one we're going to do the dx.
Okay. By the d, you mean the partial.
The partial.
Got it. So we're going to do the partial of this first one with respect to y, e to the 2y minus y cosine xy. And we're going to do the partial with respect to x of the right-hand one, which is 2x e to the 2y minus x cosine xy plus 2y. We're going to do the partial of that one with respect to x, and then we're going to evaluate and see if they're true, if they're the same. Right?
Yes, sir.
Okay. So do the partial of the left. Do this partial. Do this partial.
Sorry.
Okay.
Good now. Game's over. So that one's going to be... Actually, I'm not sure how you do that one. If it's in respect to y, wouldn't it just be e to the 2?
E to the 2y, that's a good start.
So it'd be plus sine?
Wait. Let's go back to e to the 2y. Yeah, you've done the outer function, the partial of this with respect to y.
2e to y.
Yes, you got to have the 2 from the chain rule.
I'm
Okay.
not sure I do the second part.
Okay. Guess what you're going to have to use for that?
Product rule.
Product rule. Excellent. How does that go?
F prime of x times g of x plus g prime of x times f of x.
Okay, now what's your f and what's your g?
Y would be the f. And then
Okay, that's fine.
is
So what are you
cosine
going to do
xy.
with it? Huh?
Now, is it cosine parentheses xy?
Yeah, it's cosine of xy. Okay. Same here and here. They didn't put them in the book, but that's what it's got to be. Okay. Cosine, well, they use the space there that indicates those are together. Okay.
Okay, so let's go with minus y sine of xy.
One exception. Derivative of cosine is minus sine. So that'll change that minus to a plus,
Yes.
right?
Yes.
But you still got one more thing to do before you go to the second half of the product rule, and what's that? Is it biology class again? Okay. All right, we've got 15 minutes. They just must be used to coming early. One more thing. Okay.
I'm trying to think.
You did the first times the root of the second. The root of the cosine is minus sign, so they'll change that sign. But then you got the chain rule. What's the derivative of this with respect to y? Just like you did chain rule.
X.
Yes, times an x. So it's plus an xy. Okay. So that's the first term, or the first part of your product rule. The second part, remember there was a minus there, so let's remember it's still a minus. The second part is?
It'd just be minus cosine x.
Cosine xy, perfect, okay? Because it's derivative of the y, which is 1. All right, so this is the left-hand side. I mean, this is the first partial. Let's do the other partial over here and see what we get. Partial with respect to x of that thing.
That one would be 2. Wait, you gotta do product rule, right?
Really?
Huh?
Okay. Is this a product of two functions of x?
No.
No, there's only one function of x in there.
Okay, so
The function of y is treated like a constant.
So it'd just be 4e 2y.
Okay. It's 2e to the 2y. That's your constant of x, right? If that had been 7x, it would be 7, right? So it's 2e to the y, e to the 2y x. The derivative of that would just be your constant, 2e to the 2y. So you don't do a chain rule on the y because you're not taking with respect to y, right? 2e to the 2y. Right? Minus.
With respect to x, so we gotta do product rule.
Yeah.
So minus x sine, so we gotta change that to a plus.
Got it.
Sine x of y.
Why? Why not? Okay.
Plus, no, not plus.
Minus, you're right.
Cosine xy.
Cosine xy.
Plus
2. Wait. One more thing. No, you're right. You're absolutely right. Okay.
Plus 2y.
Okay, wait. You're taking the derivative with respect to x of 2y.
I'm sorry.
And?
It just goes away.
What's the derivative of 2y with respect to x?
2yx.
Derivative, not integral.
2. 0.
0, exactly.
So,
Now, what we do now, are these two the same? Those terms are the same. Those terms are the same. And that term's the same. Yes, they're the same, so this is an exact differential. Ding, ding, ding. Okay? Now, that was just your test. You haven't even begun to solve the problem. Okay, you just verified it's an exact differential. So now you can proceed to solve the problem. Got it? No, I want you to get it. If you.
let's just lag.
What's that?
Let's just lag it behind.
Right.
We're good.
Got it? Okay. The reason I want you to have it, I need to erase it because this is going to take a while to work this one. Okay? I don't know if it'll take.
The rest of our class time.
It may not even finish. Okay? But let's do what we can.
You want me to set a timer to 1:15?
Want me to what? Do what?
You set a timer to 1:15?
Yeah, that'll be fine. Or whatever.
Why does
Yeah, because there is a class coming in after us, so we need to be out of
that
here.
lady looked pissed when she came in?
Oh, was that Miss Dr.?
No, it was the same lady that came in earlier.
Oh, okay. She can, well, never mind. Okay. All right. Here's what our assumption is. Now that we know that's an exact differential, there's got to be some function, f of xy, equal to some constant c. You know there's got to be. And you also know, now, remember you can do either one of these first and either one of them second. I just have a feeling the one with the y is going to be more complicated, so I think let's go with the one with the dx here and do that. So we know this thing here has got to be the partial of f with respect to x has to be this thing here. E to the 2y minus y cosine of xy. I don't need a parentheses if I didn't open the one, do I? Okay. Now, if that's the case, then that's going to have to be the case. So then and again, we're going to treat it as if it's only a function of x, so we're going to call this a df is equal to e to the 2y minus y cosine xy dx. We're going to write it as if it's a differential with the single variable x, and then we're going to integrate. Okay? With respect to x alone. Both sides. So this just gives you an f, and you can put down xy if you want to. Okay. Now, what's the integral with respect to x of e to the 2y?
E to the 2yx.
Perfect. Okay? That's going to be e to the 2y. I'm going to put the x in front so you don't confuse whether the x goes with the 2y or not. It's in front. Okay? That one's done.
Minus y sine.
Sine. Xy. But you sort of have to unchain rule it, right?
So would that mean we have to do integration of parts? No, that's...
No. No.
Chain rule we have to do...
Okay. Okay, now. Okay. Time out just a minute. Remember, this y we're treating as a constant because we're taking derivative with respect to it, right? So this isn't product rule problem. Okay. So you did that right. You treated that as if it's a coefficient. Okay? Antiderivative of cosine is sine, not minus sine, sine. Okay, that was right. But the antiderivative of this would be, with respect to x, would be a 1 over 1. If it was a chain rule, you'd multiply by y, since you're doing if you're taking the derivative of this, you multiply by y, since you do an antiderivative, you divide by y. So when you divide by y from there, you wipe out that one. Ooh, that's looking a little better, isn't it? Okay? But then, it's an indefinite integral, so what should go next?
Plus g prime.
G of y. G of y. Okay. Because that constant is now some function of y, because y is treated as a constant. Okay. Now, there's your fy again, f of xy. So if you take the partial of this with respect to y, we should get n of xy, right? So let's take the partial of this with respect to y. And what would that give us?
I'm sorry. I'm
Take the partial of this with respect to y.
it would be it'd just be 2e to the 2y.
The x2, x is treated as a constant here, right?
See, I thought
So
it was dx. I'm sorry.
It's a partial of x e to the, yeah. So it's 2x e to the 2y. That is the partial of that with respect to y, right?
Mm-hmm.
Minus
minus cosine xy in respect to y. So we put an
x in front, yeah. Chain rule. Okay? Plus your g prime. Right? Okay, and this is supposed to be your n of x. Woo! Here's your n of x, 2x e to the 2y minus x cosine of xy plus 2y. That was your n of x. Oh my goodness, look at this. This term is exactly that term, right? This term is exactly that term. So that leaves your g prime equal to 2y.
0.
No, g prime of y is equal to 2y. Because these went out, those went out, but you're left to 2y, right? So what would g have to be?
G would have to be, you take the antiderivative, right?
Yes?
It would be y squared.
Exactly. So g of y is equal to y squared. Okay, you don't need to put a constant in here, okay? Because we're going to come up here and plug back into where we had this before we wrote all that mess in there. And we had the f of xy is equal to x e to the 2y minus sine of xy plus y squared. And that's equal to c. Okay. It's the f of xy equals c. That's your integration constant. Is that c there? That's why we don't add one in here. That becomes your one up there. All right, let's see what they've got. It took them a while to get it to. X e to the 2y minus sine of xy plus y squared. And they've put plus c is equal to 0. I don't know why they did it that way. You could have put equal c.
Now, why is it we put the y squared in instead of putting the y g prime? Because right here, g of y, I'm stupid.
Yeah. Excellent question. No, that's exactly the kind of active participation you need to be doing. Why is that in there? Oh, I see now why it's in there. Okay.
I was looking at the g prime. I was like,
right.
G prime equals 2y, but it's
yeah.
I was looking at
the right up here you have to take out the partial with respect to y, and that.
Well, I was looking at the problem below it.
Yes, exactly.
And I was combining.
Right. I found myself doing that too. Okay, I do think we're getting close enough that we probably do need to stop. So we'll pick up next time with example 3. However, we made decent progress in this because in 2.4 exercises on just another page over or so, do any of the odds 1 through 19. Okay.
Through 19?
Say again?
You said odds 1 through 19?
Yeah, any that are in the back of the book of 1 through 19. We'll wait and do 21 and following once we've done at least one initial value problem, which is example 3, but we haven't done that one yet, so we'll do that next time. Good deal. Make sense?
Yep.
All right, good deal. And I really appreciate your coming late. Okay.
My favorite teacher. Don't want to miss you.
What's that?
You're my favorite teacher. Don't want to miss
Oh,
you.
yeah, right. As if you have more than 3. Okay. All right. Let's get this over with.